Let's start with some solved problems and some unsolved problems just to get our concepts better in our chapter equilibrium of a particle. Okay, so here we have numerical, and what is he saying to us? We look at it. Find the tensions in member BA and BC needed to support a mass of 60 kg. Okay, so there is a mass which is being placed at point D, mass D, and this mass is being fixed at point B. And tensions in member, they can be called or cable BA and BC. You need to find the tensions. So you call the tensions as TC and TA, and mass is basically 60 kg. Okay, so 60 kg mass is there, and how we will solve it? They have the first and most important thing is basically that you have to draw the free body diagram. The free body diagram is to be drawn over here. First of all, at B, if you look at it, which is the focal point where your entire coordinate system origin is resting, is that there will be tension in B, and the weight is being acting from B towards D. So as I have told you before also, what you will draw the free body diagram for this is very simple. TB will be equal to the weight, which is equals to mg, and what will be this weight TB equals to? It is must be equals to m times g, and mass is given to us as 60 kg multiplied by the gravity, which is 9.81 meters per second square. So the tension comes out to be equals to 60 into 9.81 Newton. Now the most important aspect comes that in previous lectures I have told you that you have to draw the free body diagram of your system. So B is the focal point. One cable is going towards A under tension TA. The other cable is going towards C, is going to be tension TC. And for TC, they have made our life very easy, as they have given to us the theta as 45 degrees, and for TA they have given it as orientations of the angles in terms of hypotenuse, base and perpendicular, as 3 is vertical, 4 is horizontal, and hypotenuse they have given it as 5. Okay, so this is basically going to be, and the tension most probably is basically acting downwards, as you can see is given as TB, and you have already calculated what is the tension basically is. Okay, now we proceed further. Full body diagram of the free FBD is given. 345 TC, weight is acting downwards. This is very simple. Now come the other part that you are already have got some sort of acquaintance, is to apply the equilibrium equations. So now we are going to apply the equilibrium equation sigma fx. So what is going to be sigma fx equal to? It will be TC cos 45. The component is positive. Why? Because it is acting towards the positive x-axis. Then you have go for to apply the tension in TA. TA will be basically TA into what will be, since it is sigma fx, so it's going to be TA, and the horizontal component will be 4 upon 5. But along this they have added a negative sign. Why? Because if you resolve force TA, the horizontal component will be acting towards the, by head to tail rule method, it will be acting towards the negative x-axis. So this will be sigma fx. Then you go and apply sigma fy. If you apply sigma fy for your numerical, it will be TC sine 45. Yes, the vertical component is acting towards the positive y-axis. Then you go for the TA 3 upon 5. It will be again positive because it is acting towards the plus y-axis. Then you go towards the weight, which is TB, but this time it is acting in the negative y-axis, so it will be minus TB. So you've got these three equations, these two equations, sigma fx and sigma fy. Now you have to solve TA and TC. Look, it's very easy now. TA and TC, two unknowns, and you have got two equations. So two unknowns, two equations, very easy. You can solve those as simultaneous equations to get the respective unknown. Okay, and here they have shown you the complete equations. You can solve it like this also, but you have got like advanced scientific calculators with you also. You put those equations into it and you will basically make your life very easily, and you will get tension TC is equals to 476 Newton, and you calculate it, and tension TA comes out to be equals to 420 Newton. So these components of tensions have been generated, and basically these are the unknowns that you have basically calculated it from this numerical. Okay, now we go to another numerical. They have said you need to determine the magnitude and angle theta of F1 so that the particle P is in equilibrium. Okay, now first of all, see, you need to find the magnitude. Not only you need to find the magnitude of F1, but also its orientation theta. Its orientation theta. So look at the coordinate system, xy coordinate system. The origin is lying at point P. One force is acting in the xy coordinate system, positive, first quadrant 300 Newton, orientation given as 512, hypotenuse 13. What about the other force? It's 450 Newton, its orientation is given as 20 degrees. Okay, and the other force is F1 and its orientation is theta. How will we proceed? Simple, the same logic, equations of equilibrium. The first equation of equilibrium, we will apply it as sigma Fx is equal to 0, and when we apply sigma Fx is equal to 0, it comes out to be equals to 300. The horizontal component will be 5 upon 13 and it's positive. What about the other one? Plus 450 cos of 20, again the sign is positive. What about the third one, the unknown? Minus F1 cos of theta, because if you resolve it, the x component will lie along the negative x-axis. To simplify this equation, you will get F1 cos theta is equals to 538.25. Okay, this is your equation number 1. Now you go to apply sigma Fy is equal to 0. Okay, now we will apply again the same aspects, but the vertical components 300 12 by 13, the vertical component positive. Now we go to the force in the fourth quadrant, 450 Newton. It comes out to be 450 sine 20 because it is the vertical component, but since it is acting in the opposite direction towards the positive y-axis, we add minus 450. We add a minus sign with 450 sine 20. We again go to the unknown force. It will be F1 sine theta, but when you resolve it, you see your vertical component of force F1 is going to lie in the negative axis of as compared to the positive y, so it comes out to be equals to minus F1 sine theta is equal to 0. So F1 sine theta is equals to 123.01. This is equation number 2. The first is F1 cos theta is equals to 538.25. So you've got two simple equations, two simple trigonometric equations being generated. You solve those two equations simultaneously to get, first of all, theta comes out to be equals to 12.9 degrees and F1 comes out to be equals to 552 Newton. So these are the two respective unknowns that you need to find in this system or problem, which you have basically successfully calculated it. Okay. Okay, we start another numerical. The device shown is used to strengthen the frames of wrecked autos. Determine the tension of each segment of the chain, that is AB and DC. If the force which the hydraulic cylinder DB exerts on point B is 3.5 kilonewton as shown. Okay? So basically what they have given you as there's a hydraulic cylinder DB, and then these automotives are there which have gone under a frontal collision. Their bonnet and their bumper is being damaged, and you need to basically remove those dents. This is a system to remove those dents from those automotives. Unfortunate automotives going crash, a frontal crash. Okay, so how will you solve this system? Again the same way. What I have told you, first of all, see the numerical, see the data, and build up your respective FBD, free body diagram. And if you look, you have got an XY coordinate system. Your critical point is the point B, on which your origin is lying. One is either force 3.5 kilonewton is acting, and they are giving you the other force is force BC, and then there is a horizontal force AB. So these three forces are there, and then you can see from point B they have given you vertical and horizontal respective distances. From B to C, the vertical height is given, and then the B to B distance is given to you. So what you need to do is basically the same. Apply sigma Fy equal to 0 for your system, and you will get 3.5 sine 48.37. Then this component will be positive. What about the force BC? It's acting downwards, and you can calculate the respective angle as well. It comes out to be minus force BC sine 60.95. So force BC comes out to be equals to 3 kilonewton. Now once you've got force BC calculated, now it's very simple. You need to calculate the force AB. So once you calculate the force AB, you will get sigma Fx equals to 0, 3.5 kilonewton cos 48.37, and then the force BC component, it will be for 2.993 cos of 60.95, and the unknown force minus FAB. So you have got three forces, two are already being known, and the unknown force is the force AB, which comes out to be equals to force AB 3.78 kilonewton. So you have solved this numerical in a similar way as above, and you have applied equations of equilibrium to this particle. Another numerical is there. Here we apply the system of springs. The unstretched length of the spring AB is 2 meters. If the block is held in equilibrium position shown, determine the mass of equilibrium at the point D. Okay, so you need to find what is mass at point D, and they have given you the unstretched length of AB, which is 2 meters. The unstretched length, not the when it is not being stretched. Okay, so how will you solve this system? Very simple. Here the only thing new that is the same concept will hold, but the only thing new is that a spring is there, and you know what is the spring force. Remember I told you F is equals to K times of S, or F is equals to K times of X will give you the spring force. Since they have given you the unstretched length of the spring is 2 meters, so what will be the final length of the spring? You can very easily, the coordinates are given from B to the midpoint of A is basically 4 meter, and the vertical height is 3 meters. So the hypotenuse length of that fully stretched spring will be, you can easily calculate it from hypotenuse square equals to opposite square plus adjacent square. It will give you 5 minus 2, and it will be, what is your X? K of the material of your spring is given as 30 newtons per meter, so you get the spring force as 90 newton. Okay, now you apply sigma fx equal to 0. You draw the FBD of your system x, y, and the weight is acting downwards, basically. The other component from A is basically the tension T, and the other one that you have already calculated is basically the force, which is 90 newton, and its components will basically be very simple. It will be 4 3 by 5. Okay, now you apply sigma fx equals 0. It will be T cos 45 minus 90 4 upon 5, since sigma fx you are calculating. So you calculate the unknown tension T is equals to 101.82 newton. Now you apply sigma fy equal to 0. It's a vertical component, so when you apply sigma fy, it will be minus w. The vertical components will be, for tension it will be 101.82 sine 45 acting in the positive y. And what about the other one, the 90 newton force into the vertical component will be 3 upon 5. It will be acting on the plus y axis. So you calculate it, your weight comes out to be equals to 126 newton. But in the question he is interested in mass. Now what is mass? Is W is equals to mg. So what is going to be m? Equals to W upon g. So W divided by 126 newton divided by g, 9.81. So it's approximately comes out to be equals to the mass of the block acting at D. Point D is 12.8 kilograms. Okay, so a different numerical, different approach, force calculated from the spring, and you apply the system of F is equals to Kx. Kx is the deflection of the spring, which means final length minus the initial length. So this concept, new concept arise, you should be able to grasp it as quickly as possible. Let's go to another numerical. Okay, so here if you look at it, determine the maximum weight of the flower pot that can be supported without exceeding a cable tension of 50 pounds in either cable AB or AC. So you need to calculate it, but the tension must be less than exceeding the cable tension of 50 pounds in either AB or AC. Okay, so let's see. Apply the sigma fx equals to 0. When we apply sigma fx equals to 0, the AC is equals to force AC sine 30. What about force AB? But this component in force AB will be negative, into 3 by 5. The force AC comes out to be equals to 1.2 times of force AB. Okay, and remember what is he saying, that the maximum weight of flower pot that can be, you need to determine that can be supported without exceeding a cable tension of 50 pounds in either AB or AC. So the tension in AB or AC must not exceed the value of 50 pounds. Okay, so force AC comes out to be equals to 1.2 times of force AB. Now you apply sigma Fy equal to 0. So if you apply sigma Fy is equal to 0, it comes out to be equals to force AC, force 30, plus force AB, vertical component 4 upon 5. The weight is acting downwards, minus W equal to 0. Simplify it, so it comes out to be equals to 0.8660 force AC plus 0.8 times of force AB, minus W goes on the other side of the equation, it becomes positive W plus W. Now since the failure is, since FAC must be greater than the force AB, so failure will occur first at the cable AC. Okay, because he told you that AC is greater than force AB, so the chances are it might get failure over there. So failure will occur first at cable AC with force AC equals to 50 pounds. So the tension must not exceed force equals to 50 pounds. So then solve equation 1 and 2. If we solve equation 1 and 2, we will get the solution as force AB comes out to be equals to, remember the force AC has to be less than the 50 pound force. If you solve it it comes out to be actually force AB is 41.67 pounds and the force W is coming out to be equals to 76.6 pounds. Okay, so you've got this numerical done, and you can see the force AB is 41.67 pounds. Okay, so let's go to another problem. Now we proceed with the three-dimensional system. Determine the magnitude and direction of F1 required to keep the corporate force system in equilibrium. It's a very good problem. You've got different forces acting in a coplanar concurrent system. F1 is a force basically interested in to calculate. F4 is given, F2 is given, F5 is given, and F3 is basically a 400 Newton force, and but it's given in terms of coordinates, visual coordinates and final coordinates. Okay, so F1, when you do not know any force in three-dimensional coordinate system, you will say it is a Cartesian force in three-dimensional coordinate system, called it as F1xi plus F1yj plus F1zk. Okay, F5 is given to us as F2 is given to us as minus 500 Newton. Okay, and the other force F3 is basically given as in terms of coordinates. We can basically calculate the position vector. Its magnitude is given as 400 Newton, and you calculate it as from the coordinates from the by taking a unit vector on the force. It comes out to be equals to minus 2i minus 6j plus 3k divided by the mod value of that, under root of minus 2 square plus minus 6 square plus 3 square, it comes out to be equals to F3 is equals to minus 114 I minus 342j plus 171.4 k. What about the F4 force? Is in terms of 300 Newton. It is lying in J and K systems. If you coordinate system, you can say 300 cos 30j plus sine 30k, and you got F4. And then what about the other force? The F5 is very simple. It is lying on the Z axis but negative side, so it's minus 450k Newton. So now you apply the equation of equilibrium will be very simple. It will be F1 plus F2 plus F3 plus F4 plus F5 is equals to 0. And again you apply all the I components on one side, then you add all the J components of your system, and then you add all the K components of your system, and you algebraically add them. And once you add them, you will, since all those components are equal to 0, so you equate the I components equal to 0, you equate the J components equal to 0, and you equate the K components equals to 0. Once you do that, you will automatically get your F1x, your F1y and F1z. So F1x comes out to equals to 140 Newton, F1y 543 Newton, F1z equals to 128.57 Newton. So what will be the mod of magnitude of F1 as force is F1x squared plus F1y squared plus F1z squared. So F1 comes out to be equals to 608 Newton. So but again this is given, but you also need to this F1 is orientation in three-dimensional is very important. So you already know, in order to calculate orientation of three-dimensional F1, you can calculate it very easily by using direction cosines. They have given you F1x, F1y, F1z, and you have calculated F1. So cos of alpha will be equals to F1x, which is 114.29 divided by the mod of F1, which is 607.89. It will give you alpha as 79.2 degrees. Beta will comes out to be equals to 583 divided by 607. 16.4 degrees, and gamma will comes out to be equals to 128 over 1607 as 77.8 degrees. So this this is how you solve equilibrium equations in three-dimensional coordinate system. Okay, we go to another numerical. Determine the magnitudes of F1, F2 and F3 for the equilibrium of the particle. Okay, so you have got your XYZ. This force F3 is lying on the x-axis. There is another force F2 whose orientation of hypotenuse perpendicular is given. Then there is F1 force which is lying on the x and z plane. Then there is another force, 8.5 kN force, which is basically lying in your y-axis and basically your x-axis. Okay, so how you will solve it? You need to determine the magnitude. Okay, for these forces F1, F2 and F3. So first of all you will apply sigma Fz equals to 0. If you apply that, you will get F1 sine 30, and the other one is the vertical force from the origin, which is 2.8 kilonewton, but it is minus, so it is minus 2.8 kilonewton. So F1 comes out to be equals to 5.60 kilonewton. You apply sigma Fy. When you apply sigma Fy, you will get 8.5 cos of 15, and then basically you will be getting F2 for sigma Fy will be equals to minus 24 upon 25 times of F2, which is equal to 0. You get F2 equals to 8.55 kilonewton. Now you go to sigma Fx. If you go to sigma Fx, what will you be getting over here is basically F3 lying on the positive x, and then the F1 component, which will be 5.6 cos 30 negative x-axis. What about the other one, F2, which was 8.55, 7 upon 25, but again negative, see the orientation, and then your 8.5 kilonewton, it will be 8.5 sine of 15, but minus sign because it is lying on the component is lying on the opposite side of the positive x-axis. So simplify this trigonometric equation, you will get your respective F3 comes out to be equals to 9.44 kilonewton. Okay, then this numerical I've given you. Determine the magnitude and direction of force P required to keep in the concurrent force system in equilibrium. I've given you a solution, check it out and solve it yourself. Very simple, same concepts. Okay, then another numerical is there. If the bucket weight is 50 pounds, determine the tensions developed in each of the wires. Okay, so it's a good problem over here. If you look at it, you need to calculate the bucket is given as 50 pounds. You need to develop the tensions in each of the wires, which means tension in AB, tension in BC, tension in BE and tension in ED. You have to calculate the tensions. So what you will do, you will very good numerical, you will apply the concept at point first of all E. You have two coordinate systems over here. First is the E. At point E it will be the weight acting down, the FPDA, then force EB and then the force ED. Angles are given 30 degrees and 3, 4 by 5. The hypotenuse is given as 5, perpendicular 4, horizontal is 3 for the orientations. Okay, you apply sigma Fx over here equal to 0, you get force ED cos 30 and force EB 3 by 5 as the horizontal components. Apply sigma Fy, you get force ED sine 30 plus force EB 4 by 5 minus 50 equal to 0. Solve those two simultaneous equations, you get force ED as simple 30.2 pounds and force EB is 43.6 pounds. Now you see the common junction between the coordinate system at E and B is the force EB, which was 43.61 pounds. You apply the same concept over there at FPD-B. If you look at it, force EB comes out to be equals to 43.61 pounds. Then at point B there is force BC, and point B there is force FA. So again, if you look at it over here, is basically you have got two unknowns. You know what is force EB, and so your two unknowns will be force BC and force BA. Apply sigma Fy, you will get force BC sine 30 minus 43.61, 4 by 5. You get force BC is 69.8 pounds. You apply sigma Fx equals to 0. And when you apply sigma Fx equals to 0, you get 69.78 cos 30 plus 43.61, 3 by 5, minus the unknown force component FBA, which is acting on the opposite side of x. So you solve it, and you solve it, you get force BA equals to 86.6 pounds. Okay, very simple problem, but a new concept. You have to apply. So many unknowns were there. Why you do it? Because you've got so many unknowns. You have basically got two coordinate system, because you need to calculate force EB, you need to calculate force ED, you need to calculate force BC, you need to calculate force BA. So 4 unknowns were there. So one coordinate system will give you 2 unknowns, like at first acting at A, FBD A at point E, and then the second coordinate system acting at point B gives you the remaining 2 unknowns. So different question, different approach, just to enhance your knowledge concepts further in this chapter. Now, students, I want to give you that I have taught you the theory, I have taught you the fundamental concepts, I have given you quite a many problems, 2-dimensional problems, 3-dimensional problems, solved it in front of you, given you the rudimentary concepts. So I want you to solve these homework problems for me as well. You will be graded for this, and try to do it in the most professional way. Problem 3-32, very similar to the one I've just told you, but slightly different. Okay, approach, you have to be very cautious how you solve this. And then there's another problem. The bucket and its contents have a total weight of 20 pounds. Determine the force in the supporting cables DA, DB and DC. Okay. The top one is basically a 2-dimensional problem. The bottom one, or the bucket, is basically a 3-dimensional problem. Okay, so you have to solve it, and I will ask you for the solutions. Okay, and then another problem. I have given sometimes this problem in the exam as well, so I want you to solve it. Very important problem. Determine the forces in cable AC and AB needed to hold a 20 kg ball D in equilibrium. Take F is equals to 3 Newton and D is equals to 1 meter. Okay, so you solve it, and I will ask you for this solution. And then in the end, I will basically be asking you to sincerely review what you have done in this whole chapter. Okay, so this review will tell you the concepts in everything you have missed, like what is a particle equilibrium, how you apply the particle equilibrium as resultant of all forces sigma F equals to 0. Okay, that is how you apply the particle equilibrium. And then if that equilibrium is a 2-dimensional system, you can see there is a cable acting on a pulley, how you apply it, and if there is a spring, what equation you use, like F is equals to Ks, and remember S is the deflection, it will be final deflection, final length minus the initial length. And if there is a cable, you will apply tensions in that system, sigma Fx equals to 0, and remember the cable will always be under, the cord will always be exhibiting tensile force, never you will take it as compressive force. Developed in the continuous cable passes over a pulley, and remember that there will be no friction in your pulley. It must have a constant magnitude throughout the cable to keep the cable in the equilibrium state. So if the problem involves a linear elastic spring, then the stretch or compression, and remember, if there is extension in the spring, it will be positive. If there will be compression, you know it will be negative. Just to tell you knowledge, enhance your knowledge. Then you go for your 3-dimensional system. If you go for your 3-dimensional system, here you can see if you have solved many numericals, you have F1, F2, F3, 3 different forces are acting. And if the 3-dimensional geometry is difficult to visualize, then the equilibrium equation should be applied using Cartesian vector analysis. You know what is Cartesian vector? The force in unit vectors, sigma fx xi plus sigma fij plus sigma fzk. And if the scalar force, remember, it will be just a magnitude. F equals to 300 Newton, F equals to minus 40 Newton, F equals to 800 Newton. This is scalar force. Cartesian will be in terms of unit vectors, fxi, fxy, j, fxn. Always write your force in. It's a good practice to in Cartesian vector form. That is the best practice. You should always apply in solving your numericals. Okay, it's a very good healthy practice. R.C. Hibbeler follows it. If you look at other books, reference books that I have shown you in my link, they also follow this thing. Until unless they ask you in the numerical to calculate the scalar force, then you do it. Otherwise, you always go for the Cartesian vector force. So when the forces are here, they have got sigma f equals to 0. So you apply sigma fx equals to 0, sigma fy equals to 0, and you apply sigma fz equals to 0 in a three-dimensional coordinate system for forces as shown in the figure, x, y, z, three unknown forces, and these forces are basically acting in a plane of three-dimensional coordinate system. Okay, so with this basically we finished the chapter. We understand the theory, we understand the fundamental concepts, how the equations are applied, how FBD is applied, and I've shown you two-dimensional coordinates, a system of equations applied to various particles, and then three-dimensional equations of equilibrium applied to three-dimensional systems, and I have given you numericals. I have shown you, I have also given you some homework problems, and I hope you will understand those concepts first and then apply it and be able to solve the numericals correctly. And if you have any problems regarding what I have shown you, you must always go to the book and see my notes that I have given you. The book and these these e-notes, what I say as any problem. And again, if you still don't understand, you are always very much welcome in my live session, and I will try to solve all your queries so that you'll able to understand and the concepts of the engineering mechanics more professionally, and it will help you grow as a professional engineer. Okay, I say goodbye, and then we'll go for the next chapter. Thank you very much, students. Best of luck. Allah Hafiz.